Hello again, AC Science students on track A. We're looking today at Wednesday, January 13th. Main goal today is to get going on that Tectonic Investigation 6. So kind of looking at the calendar, today is Tectonic Investigation 6. We will have a day when we come back together on next Tuesday. Again, on Tuesday, that's going to be all of you track A folks plus all the track B folks together in class. And that'll be kind of a day to kind of catch up and make sure we've got Investigation 6 all solid. Ask your questions. If you have questions or aren't sure on what you need to do on certain parts, make sure you have those ready so you can ask them on that day. And then Investigation 6 is due by Thursday, January 21st. So Thursday next week. So you've got about a week to get this thing done. Plenty of time. Get it done, ready to go for class on Thursday. So before class starts, you want this done, ready to go. So on Thursday, we're just going to run through and answer the questions and make sure we've got the correct understanding, because the quiz on this stuff coming up on Friday of next week. We got a little time. So diving in, taking a look at Investigation 6. We're going down here to what's under our feet, and I just clicked a little more arrow next to Lehigh Tectonics Investigations here, and Investigation 6. I got it all loaded over here. Again, with all of these investigations, follow the instructions. You want to make a copy of this question sheet, Google Doc, and then just follow the directions. Don't try and answer the questions. Try and follow the directions. That is the important thing to do as you work here. So kind of looking up, there is kind of two parts to this. The first part deals with subduction zones. So subduction zone is kind of the place where one of those plates slips underneath the other and sinks back and turns back from crust into that asthenosphere. It changes from lithosphere into asthenosphere, from crust back into mantle, whichever words you prefer to use. It melts. It changes from rocks like we are used to seeing them to that kind of mushy, sludgy, movable, not breakable rock of the asthenosphere. So it's not rocks like we know. So part one deals with kind of that process and what features are created on those places. So the first part here, step two, is to identify and trace the plate boundary. When we are looking for subduction zones, we are looking for deep ocean trenches is the name of these things. And they have you looking at one called the Aleutian Trench. It's up near Alaska. Aleutian is related to the native folks from Alaska and that area. They do have you exploring this elevation profiles again. We've worked with those before. They've drawn some in there for Investigation 6. Notice this one does have some that goes above, kind of across the island. So it's above sea level as well as some below sea level. So check out those things, see what's going on there. Again, follow the directions. And then they have you tracing. So again, as you follow the instructions and are answering the questions, trace along the elevation profile. Go look at that volcano. There's lots of volcanoes in here. There's a screenshot from map from step 2K. So if I'm looking in the instructions here, step 2, here's letter K. So that's where it has you do that. Again, you can do a screenshot. You can use the export map tool. It's up to you. But get that into your document. Okay. When we get to step 3, that's right, they do have some really nice videos in here of kind of the plate motion and showing what's happening at that subduction zone. Step 3 is about determining the slope of the subducting slab. So one of the really cool things that we can actually do as you work through is you will be able to map the subducting slab. So as we look at the Pacific plate and the North American plate, the Pacific plate being the heavier one, kind of sinks underneath the North American plate. So this one here is going to be the Pacific plate. We can actually measure where that is, and there's some really cool work being done right now mapping these plates that have subducted and are underneath, because it does take time for it to change from that continental, or from that crust, from that lithosphere back into a asthenosphere or mantle. So it takes time, and so we can actually measure where that is. It's super cool. As you look at the earthquakes and where they're at, and talk about, there's so many cool things to do on this, and actually see that underground is really kind of a cool thing to measure. And then of course we can measure how fast that's subducting, and so that different places it's happening at different speeds, and so we can look at that kind of those rates of that subduction and how fast it's sinking back. And here they get into kind of age of the ocean floor, and age of the ocean floor is going to be connected to how fast it subducts, how fast it sinks back and turns back into the mantle of the asthenosphere is related to how old the ocean crust is. Okay, so really cool stuff with subduction. It's a really fascinating process, and you can actually map out and see where it's happening, which is super cool. The other interesting thing that happens at convergent boundaries, the ones we're looking at today, is they create some pretty significant landforms. In particular, mountains of different sizes and shapes, as well as volcanoes. So they have you kind of exploring some of these landforms. Again, some really nice pictures in here. It's just too bad you can't make them bigger, but kind of exploring those and looking and seeing and thinking about kind of where those are and where those are coming from. The next area they have you look at a little bit is the Pacific Northwest. Again, looking at that Juan de Fuca plate as it's slipping underneath and subducting underneath the North American plate. It's got a divergent boundary with the Pacific plate and is subducting with the convergent boundary underneath the North American plate. Again, line of earthquakes means plate boundary. Line of volcanoes means that the plate boundary is also a convergent boundary. The last thing they have you come look at is exploring continent collisions. So kind of so far in this investigation, we mostly looked at oceanic versus continental crust, or oceanic versus oceanic crust. And we talked about a little bit about that earlier today, or yesterday, I guess for you it is now, in that the oceanic crust is primarily made of basalt, and that's a more dense rock, whereas continental crust is typically made out of granite, which is a less dense rock and has some different properties. But when continents collide, as does happen, continents also collide. When oceanic and continental, ocean and ocean crust, one of them is always going to subduct. But when continents collide, you got granite and granite, continental crust and continental crust. When those things collide, what typically results is mountain building. And so this looks at the collision in particular between North America and Africa. So again, we get those continent outlines back, and we kind of play that back and go look at some nice pictures of that mountain building. What happens when continental crust interacts with continental crust? Again, some more elevation profiles. Look and see kind of where is that and what's happening in that particular area. So lots of cool things happening. Again, it does kind of break into a couple of parts. Subduction is a super awesome and interesting process where one of those things sinks back down. Typically an oceanic crust sinks back down. But we also look at that continent-continent collision and what happens when two continents colliding, like it's happening in several other parts of the world. So work through, follow the directions. At the bottom, you do, of course, have the tutorial video as well as the features video. Definitely check those things out if you're struggling. So if you get stuck and be like, oh, I couldn't do it. No, go watch the videos. They're here for you. Come watch them. Go learn about them, and they will walk you through how to do this stuff. So please don't come like, I didn't know how to do it. If you come with specific questions, I didn't understand how this works, definitely do that. Awesome, great. But if you're like, oh, I just didn't feel like doing it, no. Go try. You've got time now. Go try. And if you're stuck, check out the videos on here. They will walk you through how to do this. Okay. And of course, if you have other questions, please make sure you ask. Okay. Kind of heading back to the calendar here. Final reminders. Looking at today, Wednesday, January 13th. Good time to look for the moon today is going to be kind of, or shifting toward that early evening, kind of right after sunset. It's going to be real hard to see the moon right now during the daytime. It's only a little teeny tiny sliver. But if you look right after sunset, that's going to be the best time to look for the moon and record those observations in your notebook. I think we're looking at building a nice record. And so if we can have some nice observations recorded in your notebook, kind of Q4, we'll hit that and tackle that. And put those observations together. But make those observations now when you can, right after sunset. I think moon sets today at about 5:30 or so. So I mean, just after sunset. So make sure you get outside and check that out if it's clear enough. Hopefully you can see it. Otherwise, have a great day, folks.